Hello everyone. In this very first session, I want to shortly introduce two concepts, verification and validation of a numerical simulation. So, verification is simply when we evaluate our model's prediction based on the mathematics of the model. So, we want to make sure that the solution that we provided for a physics of a problem is mathematically correct. And in the validation, we want to make sure that it follows the physical assumptions and the physical meaning of our problem. So we want to make sure that our predictions is almost the same as our experimental measurement. So I prepare a very simple example here. So imagine that this is our problem. We have a beam. When the force is applied at the tip of the beam with a value of F, and the deflection of beam is W, and the Young's modulus of the beam is E, the second moment of the area is I, which is equal to the double integration of z power of 2 d greg dz, and mu is the mass per unit. So we have two boxes here, verification and validation. So this is our two box. So I start with verification. So for verification, we know that the equation of motion of beam is like this. So we have a fourth order equation of motion. So it's a PDE when the loading is Qx for a general form, and when the deflection is W as a function of x. So we have a Young modulus, and we have also Q in this equation. But we can neglect the acceleration term, so we can consider as a static deflection. So we consider a static deflection, and then we solve this problem with numerical solution. So when we want to solve this problem with numerical solution, we can consider a very simple case in which we have an analytical solution. So in this case, we have a clamped boundary condition, and we have a force, a vertical and pointed force like F, and we want to compute the deflection at the tip of the beam. So in this case, the analytical solution is W equal FL to the power of 3 over 3 EI. Then we want to solve this problem with our numerical solution. For instance, we want to use finite difference method or finite element method. Then we want to make sure that our method works well, our solution. So the first thing that we want is we build our FEM, for instance, and then we write a code, and then we reduce the mesh element, the element size, and then we see that the element size is this is DOF and this is W, and we may see that by increasing the element size, by increasing the number of elements, it converges to a certain value, and this certain value is should be equal to W FL 3 over 3EI, the analytical solution that we had. So we can say that it's verified. For validation, we make sure that our solution is equal to the measurement. For instance, this is our setup, the experimental setup. We have an I-beam here. We have a welding here at the to join the beam over a plate, and the plate also is steel. So we may have a deflection at the welding, at the joint, and also at the boundary condition. So it's not completely clamped boundary condition, so we may have a deflection. And also we apply a force by adding a mass m at the tip of the beam, and we measure the displacement at the tip of the beam. So we trace we plot the force displacement curve, and then we we add our simulation prediction to these curves. Then we can compute the displacement of the experiment and simulation, and we can compute the error between these two. In fact, it's not error, it's relative difference between these two. And then we can say that our simulation has, for instance, 10% relative difference with respect to the experimental measurement. So in this case, our validation metric is the displacement at the tip of the beam. So this is our validation metric. So we define W as our validation metric. Or we could also define different validation metric. For instance, I could insert a strain gauge here, and then I could measure the epsilon E11. So here is a bending, so here is a E11 is a tensile, so I could measure epsilon 11, and then in our in my FE simulation here, so for instance, if this is my simulation like a rectangular cross section, then I had node here, so I could compute the epsilon at the integration point, and then I could compare these two epsilon as a different validation metric. So it depends on our application what we want to define our validation metric. So this was the verification, and this was validation. And then when we validate and verify our simulation, then we can use it in our application. So thank you very much to see this video.